Hello, this is Josiah Winslow recording for his Data Structures and Programming course at MATC for instructor Mark Cribb. Now, this assignment is on binary search trees. A binary search tree is basically a tree with binary nodes in order that's convenient for searching. Makes a lot of sense when you think about it that way. But more specifically, a tree is a data structure with a root node and branches that lead to other nodes, which themselves can lead to other nodes, and so on and so forth. And each node has its own height within the tree. It's a hierarchical data structure. And a binary tree is basically a tree that can have up to 2 branches per node. It can have either 0, 1, or 2 for any given node. And a binary search tree is different from a binary tree because its nodes are in order. That is to say, for every node to the left of it is less than it, and every node to the right of it is greater than it. And that makes it very convenient to search for a value in it because the complexity of that, as opposed to O of n, having to search through the whole list, is O of log of n. We can basically cut out half of the list in every iteration of the search. So I will get to how I implemented one in Python, and I actually did something a little bit extra. I was able to make a self-balancing binary tree, which can guarantee O of log of n for insertion and deletion as well, because the tree might get out of balance, and the worst case scenario is that the tree is entirely, heavy to one side, and it's just, like a singly linked list in that way. But if you have a self-balancing tree, it will correct itself and make it so the height is basically as small as it can be. So this class right here, BSTree, is what I called it, and it doesn't really do almost any of the heavy lifting. Aside from a few helpful dunder methods, all I have in the BSTree class is insert, delete, index, and that's about it. And all the insert and delete methods do is call the insert and delete methods I set on the node class and store the result back to the root. That's the only thing this keeps track of, really. So I'll explain what I do for the nodes. Now, these are nodes to what are called AVL trees. An AVL tree is basically a binary search tree that also has each node keep track of what is called a balance factor. I've named it BF, and it stands for the balance factor, which is basically the height of the right subtree minus the height of the left subtree. So you can get kind of an idea of how out of balance this node is. If it's 0, it's perfectly balanced. If it's 1, it's right heavy. If it's -1, it's left heavy. And anything out of that range is out of balance. And if it does get out of range, we have to bring it back into balance using a process I'll explain later. So the important methods here are insert and delete. And I'll explain the insert method first. So if we try to insert a value into a given node and its sort of subtree, if that value is equal to the node's value, we do a runtime error because the node already is present in the binary search tree, and I didn't bother to implement a way to insert duplicates. And if the value is less than the value of the node, then we go to the left, otherwise we go to the right, and we basically do this. We create that subtree if it doesn't exist, and if it does exist, we recursively insert that value into that subtree. And also all these lines with BF, old BF, stuff like that, this is all just math with the balance factors to keep track of everything. Because, fun fact, you don't actually have to know the heights of the left and right subtrees to calculate the balance factor once you do one of these operations. And then after we do the insert, we call the balance method, which brings it back into balance if it's out of balance. I'll explain that later. And here we have the delete method. So, if the value is less than or greater than the value of this node, then we go into that subtree, and if that subtree doesn't exist, we do an error because the node we're trying to delete is not in the tree. But if it is, we recursively delete it and keep track of the balance factors. However, if this is indeed the node we are trying to delete, then we have one of 4 different cases that we have to deal with. And these 4 lines right here deal with 3 of them. That's when the node either has 0 children, or it has only the left or only the right child, in which case we can just replace the node with that child. However, if the node has 2 children, then we can't really delete that node unambiguously. So what I need to do is I need to find the maximum value in the left subtree, which basically means I go left once and then right until I can't anymore. And then I take that value and then swap it out with the node's value that I'm trying to delete. So that way, we can still, delete a node with that value and have the tree still be in order. Because otherwise, it gets very, very awkward. So I take out the maximum from the left subtree. I put that at the root that we're trying to delete, and then I go into the left subtree and then I delete that value that I just got out and keep track of the balance factors. And then afterwards, I make sure the tree stays balanced. And here's how I do that, by the way. There are 4 different cases for the balance factor being out of whack, and we have to deal with that with 4 different sets of tree rotations. We have to do it either once or twice. And those will bring the tree back in balance. This is a constant time operation, more or less. And the rotate left and rotate right operations are very, very simple. Let's say that B is the right child of the node. We replace the right child of the node with B's left child, and we replace B's left child with the root. And that will restructure the tree such that it stays in order, but it goes back in balance. It changes its balance. Then I do the math of the balance factors and then return B as the new root. And the rotate right operation is symmetric. And that is basically all there is here. This string method, by the way, I adapted it from an answer on Stack Overflow, which, let's see if we can take a look at it. Yeah, so they did a pretty neat visualization of a binary tree that I was able to use, but in order for me to feel comfortable using it, I had to change it from looking like this. But anyways, the test suite that I made for this is very, very simple. This is very similar to what I did for Assignment 3 with the linked lists. I have a very limited set of operations we can do to the tree. We can display it, count its nodes, search for a value in it, insert a value, delete a value. And I also did get item and set item at a certain position because why not? And then quit. So let's go ahead and initialize this tree with an iterable that absolutely means nothing, so don't even try recognizing it. And there we go. And you can see that this is the string visualization of that tree. And by the way, this is balanced, so that means that the height of the right subtree and the height of the left subtree for every node doesn't differ by more than 1. And then this is the representation as opposed to the string representation. So let's go ahead and count the nodes in the tree, and we have 27 different values, 27 different nodes. And let's say we want to search for a specific value, like let's say 69. And we found it. Nice. And you can probably see up here how that happened. So 69 is greater than 9, so we go to the right. It's greater than 35, so we go to the right. Less than 84, we go to the left. Greater than 64, right. Less than 83, left. 69, we found it. And we can also search for a value that doesn't exist, like 31. Yeah, 31 was not found in the tree. So you can probably see why. Go to the right because it's bigger, smaller, bigger, bigger, smaller. Whoop, there's nothing there. All right, now let's insert a value into the tree, like 137. And then if we display the tree, as you can see, it changed a little bit. And the structure of the tree, by the way, has changed because 95 used to be the root right here. Now it's 97, and 137 had to be inserted over here. That's a consequence of the balancing that I did to it. And let's see, what would be the most interesting node or set of nodes to delete? I suppose it would be kind of interesting to delete node 84, the node with the value 84. All right, so we delete it from the tree. And would you look at that? Now that's gone. And let's also delete 83. And then now we see what happened to this set of values right here. All this, by the way, to keep the tree back in balance. And the last things that we're going to do is get item at position and set item at position. And I made the position, by the way, dependent on the sorted order. So 0 would be at the 0th position here, 1 would be at the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, and so on and so forth. So what should be at the 4th position is number 4. What should be at the 11th position is number 23. And this goes on like this. And let's also do the set item at position. What I made that do is I made it delete the item at that position and then add whatever value you're setting. So position of value 11, let's delete the 23 and replace it with 32. All right, and by the way, this also will re-index everything so that everything's in sorted order again. So instead of 23 being right here, right next to the 15 and 27, that gap is right there, and the 32 was inserted into its proper spot. All right, and that is it. Now let's tear this tree apart. Actually, you know what? I'm not going to delete every value in the tree. It's going to take too long. But it is pretty interesting to do it automatically on your own because I just love how the tree changes structure as it tries to rebalance after deleting everything. That'd be pretty fun to try yourself. But with that out of the way, Thank you so much, and I will have probably a fun time implementing the hash tables assignment, when I'm doing that next. Take care.